All right, good afternoon. Let's get started. So, wow, we're getting smaller and smaller each time. Down to 5. Good. So my plan is that we're going to go over one example is partial fractions, but if you feel comfortable with it, then we can skip that exercise. And then we're going to look at a couple examples solving differential initial value problems using Laplace Transform. I think will be similar to most of the questions on the homework if you take a look at the problems. So any questions before we get started? No? All right. Shall we look at an example on partial fractions? Yeah? Okay, great. Yep. Let's just do a kind of a quick review on it because I'm pretty confident that, when you use the Laplace transform, especially for the problems in the homework, you're going to have to use partial fractions at some point to figure out the final solution. So let's look at this example. Find partial fractions of this fraction x squared plus 15 over x squared plus 6x plus 9 times x squared plus 3. So last time I give you this, but in slightly different form. So the first thing we have to do before we writing down the general form for the partial fractions, we're going to have to factor the denominator as much as possible. At the first factor in the denominator, x squared plus 6x plus 9, we can factor that into x plus 3 squared. And at the second one, nothing we can do, just leave it. The numerator stays. And from here, we can try to figure out what the partial fractions that we can get out of this fraction based on the factors in the denominator. So we have a linear factor, x plus 3, that's a linear, but it has a power of 2, so that means we can get 2 simple fractions based on that part. And then we also have a quadratic, which will give us, which cannot be simplified, so we're going to have another fraction just for that factor. So in the end, the general form for the partial fractions will be x plus 3 as a denominator, but there are 2 of them, so we're going to have to write x plus 3 squared as a different denominator. Then the quadratic just goes by itself, x squared plus 3 as a denominator. And then we write down the numerator. We have x plus 3, it's a linear, so the numerator will be a. X plus 3 squared is still a linear factor with power 2, so the numerator is going to be b. And then the last part, we have x squared plus 3, so the numerator will be cx plus d, because that's a quadratic factor in the denominator, so the numerator should be linear. So from here, we can try to find any constants that's easy to find. I'm not going to do it here just to save time. I'll do it later with another example. So the only constant that we can find easily is finding b. If we multiply by x plus 3 squared to both sides, we can solve for b very easily. We couldn't find a that way, we couldn't find c or d. But let's just solve for a, b, c, d systematically. So we're going to multiply the equation, well, forget about the most left expression. So from the middle here, we're going to multiply that equation by the denominator on the left. So we're going to multiply by this denominator. So multiply by x plus 3 squared, x squared plus 3 to every term in the equation. If I do that, I hope you are comfortable with, so I end up with, on the left, x squared plus 15. because the denominator is being cancelled when I multiply by this factor. And the right-hand side, at the a term, one of the x plus 3 will cancel. So I get a times x plus 3, x squared plus 3. Right? And then the b term, both x plus 3 factors will cancel. So that's a b x squared plus 3. And then the cx plus d term, nothing cancels. So I have, oh sorry, not nothing cancels. The x squared plus 3 will cancel. So I have cx plus d times x plus 3 squared. Okay, so we get one equation. So the next thing, we just expand everything in there. So I'm going to FOIL this product, but as well as when I've done that, I'm going to distribute the a into every term there. So this will give me x squared, give me x cubed, so that's ax cubed. X times 3x, so that's a 3ax. And the 3 times x squared times a, so that's a 3ax squared. And the 3 times 3 is 9, so 9a. The b term, so that's going to be bx squared plus 3b. And then the cx plus d term, you might want to do a little bit extra work on the side, figure out x plus 3 squared first. So that's x squared plus 6x plus 9. So multiply with cx plus d. Let's just multiply with cx first. So that's a cx, x squared, cx cubed, cx, 6x, so 6cx squared, cx 9, so that's a 9cx. And then multiply everything by d, so dx squared plus 6dx plus 9d. So that's the right-hand side. The left side, I have something. So this is kind of similar to what we did with the judicial expressing. When we plug in the ansatz, we have to look at both sides to make sure the coefficients are the same. So we're going to do the same thing here. We're going to group the like terms on the right-hand side. So that's going to give us, I'm going to group all the x cubed terms. So that's let's see, we have ax cubed, cx cubed, that's it. So we have a plus cx cubed. Then we're going to group x squared terms, so that's going to be 3ax squared, bx squared, 6cx squared, and the dx squared. So this is 4 terms there. So that's going to be 3a plus b plus c plus 6, sorry, plus, oh, lost track. 3a plus b plus 6c plus d x squared. Then we're going to look at all the x terms. So we got 3ax, 9cx, and 6dx. So 3ax, 9cx, and 6dx. So that's going to be 3a plus 9c plus 6d times x. And then we're going to move all the constants. Doesn't have any x, so 9a, 3b, 9d altogether. Just use the addition. So 9a plus 3b plus 9d. All right, once we have all the like terms combined, grouped together, so we can look at both sides of the equation. For the same terms, we want the coefficients to be the same on both sides. So here we have x cubed, but on the left side we don't have x cubed, which is okay. We're just going to assuming it's a 0 times x cubed. So we want the coefficients to be the same. So we get 0 must equal to a plus c because we don't have any x cubed on the left. Same thing with the x squared. We have 1x squared on the left, so 1 must equal to 3a plus b plus 6c plus d. And then the x term, we don't have it on the left, so it's a 0. to begin with. So 0 must equal to 3a plus 9c plus 6d, and then constants. So 15 must equal to 9a plus 3b plus 9d. So we end up with 4 equations, which is good because we had 4 unknowns that we were solving for, a, b, c, d. So if you end up with 4 unknowns, but you only have 3 equations, that means something is not right. And I'm not going to solve this in front of you. It's going to take a while, but you can definitely try to use substitution, because from the first equation we know that a equals negative c. You can put in there, so that will reduce those 3 equations to be b, c, d. After you put a here, you can solve for c or solve for d. Use it as a substitution in other equations. Is it okay if I don't solve it? Okay, but anyway, I'll give you what they are, so if you are interested, you can work on it on your own, but I'm sure you have a lot of practice in the homework problems. So at the end, a equals 1/2, b equals 2, c equals negative 1/2, d equals 1/2. Okay, so now we can actually write down the partial fractions for the given fraction. So let me just write down what I have. So I have x squared plus 15 over, it doesn't matter which one we pick, x plus 3 squared, x squared plus 3, and that's going to be a, which is 1/2 over x plus 3, plus b, 2 over x plus 3 squared, and the cx, so that's a negative 1/2 x plus 1/2 over x squared plus 3. I just want to point out one thing, that I usually prefer to write it this way. You know, having the a, even though it's a fraction, having the fraction in the numerator. Or could write it as 1/2 times 1 over x plus 3 plus 2 times 1 over x plus 3 squared. And then the last fraction, you know, there's not much we can do other than just splitting them. So we can split that. In fact, we're going to have to do, if we do end up with this, when we use the Laplace Transform, we do have to split this into 2 fractions. So we can write it as negative 1/2 times x over x squared plus 3 plus positive 1/2 times 1 over x squared plus 3. So I prefer to write either like this or this way. I don't like, so this is what I don't like to write. I don't like to write as this one as, I do not like to write as 1 over 2 times x plus 3. Because if you, there's nothing wrong with writing it this way, and a lot of times we prefer to put it in this form. But when we use Laplace Transform, if you put it in this form, you're going to have to separate the 2 from the denominator in the process when we apply the inverse Laplace Transform. So it's not very helpful to write like this. It's a little easier, I think, to put it in this form. But again, it's still whatever you prefer, really. So not preferred. Does that kind of make sense? To just make it easy, I think. Any questions about partial fractions? Alright, if not, I guess we can jump into the exercise with Laplace transforms. We're going to use it to solve initial value problems. So the first one will be, we're going to solve y double prime equals y with initial conditions. Y of 0 equals -1, y prime of 0 equals 2. Let me ask you, do you all have a table of Laplace transforms in your notebook? Is it okay if I don't write them? Okay, good. And I'm sure you all have like a sine and a cosine in the table, right? Okay, good. So that will be your, you can refer to that multiple times when we're solving this. So to solve this using Laplace transform, the first step is just going to take the Laplace transform of the given equation. So Laplace transform of y double prime equals y. In the future, you can probably skip that step. And then we're just going to take the Laplace transform of each term there. So the left side is Laplace of the second derivative, the right side is the Laplace of y. And then now, obviously we're not going to derive that. We can just go to the table and then look for the Laplace transform of y double prime, and then look for this from the table. So the next step, according to the table, is it okay if I just write down what I have? Okay, but you can refer to the table. So that's going to be on the left side, the second derivative Laplace transform gave me s squared capital Ys minus s lowercase y of 0 minus lowercase y of 0 derivative, the y prime, evaluated at 0. And on the right side is just capital Y of s. And then the next step, so that's the first thing. So now what we do is when we take the Laplace transform, we get rid of the differential equation. There's no first or second derivative unknown constants. We have constants here, so there's a function of s and y, factor y. So now we're going to plug in the initial conditions. So plug in initial conditions. So this y of 0 becomes -1, y prime of 0 becomes 2. So that gave us s squared capital Y of s minus s times -1 minus 2 equals y of s. I'm just going to rewrite this as positive s. You can write a new line. I'm being a little bit lazy here. So that's the first step. The second step is usually the easiest one. So we're going to solve for capital Y of s. Before I do that, I do want to kind of go back to the problem to note what we're looking for. When we see solving initial value problem in the beginning, like y double prime equals y with those initial conditions. So what we're looking for is that at the end, we want to find lowercase, because that's a differential equation with lowercase y, right? So we want to find lowercase y of t, or maybe y of x. That's what we want to find. But once we convert it into Laplace transform, we're not going to have y of t, so that's why we end up with y of s, which is the Laplace transform of y of t. So this is Laplace transform of y of t, of the solution that we're looking for. So let's solve for this first, and then maybe from this y of s at the end, we can find out y of t. That's what we're looking for. So if we solve for y of s, we have, I'm just going to move the right side to the left, move s and the -2 to the right side. So we get s squared y of s minus y of s, and then move the two terms to the right, so we get positive 2 minus s. And then we're going to do a little bit of factoring, really group the like terms on the left. So we get s squared minus 1 y of s equals 2 minus s. So we always solve for capital Y of s. Even though we have s in there, but we're not solving for that. We're solving for y of s. And then we're going to divide by the parentheses part, so we get y of s equals 2 minus s over s squared minus 1. So we found the solution, but it's not in the correct form, it's in the Laplace transform form. So step 3, we need to use inverse Laplace transform. So find y of t using inverse Laplace transform, because y of t equals inverse Laplace transform of capital Y of s So if we do that, so y of t is equal to inverse Laplace transform of capital Y of s we know from the previous step, so that's going to be 2 minus s over s squared minus 1. So here again, we can try to use a table. So if we go to the table, we look at the right-hand side. Say, does any of the s functions look like this, with particularly the denominator, s squared minus a number? So if you look at the table, so I believe you have s squared plus k squared as the denominator, and then you have s minus a or s plus a, doesn't matter, as the denominator. But I don't think we have anything that's like an s squared minus a number or s squared minus k squared as the denominator. It's just not there, right? So this is the case that we have to do something. We have to manipulate this fraction to get something that's familiar to us. So we need the partial fractions. So use partial fractions here. For this fraction, so we need to factor the denominator, so 2 minus s over s squared minus 1, that's s plus 1, s minus 1. So the partial fractions from here will be, one denominator is s plus 1, another one is s minus 1, with a and b as the numerators. Let me ask you this, do you feel confident to find a and b from here? Okay, so I'm just going to do it quickly. I'm going to find a using the method I use, and then I'm going to just give the value for b. So to find a, instead of multiply by this denominator to both sides and then expand, finding the equation for a and b. So what I do is I just multiply by the denominator of the a term. So multiply by s plus 1 first to the equation. So I get 2 minus s over s minus 1 equals a plus b over s minus 1, s plus 1. And then I'm going to plug something to make s plus 1 0. So I'm going to plug in s equals negative 1. So make s plus 1 equals 0. So plug in s equals negative 1. So if I do that, a term by itself, so that doesn't change. This part doesn't have s plus 1, so it doesn't change. But this term, because we have s plus 1, if we make that 0, that's going to go away. So we get 2 minus negative 1 over negative 1 minus 1 equals a. Turns out to be negative 3/2. And if you follow the same before I do more stuff, does that make sense? You've probably seen this before, right? Okay, good. Excellent. So if I do the same thing, I end up with b equals 1/2. You can try it on your own, but just to save time, that's what I have. Okay, so now we found the two partial fractions. I'm going to put it in the form that I prefer. So that's going to be a is negative 3/2. So negative 3/2 times 1 over s plus 1. And then b is 1/2. So 1/2 times 1 over s minus 1. Just to separate the coefficients from the fractions. Now I can go back to find y of t. So recall that y of t equals inverse Laplace of this fraction, but that's being replaced with partial fractions. So negative 3/2, 1 over s plus 1, plus 1/2, 1 over s minus 1. And I can take the inverse Laplace of each one of them, and then also kind of pull out the coefficients. So that's going to be negative 3/2 inverse Laplace of 1 over s plus 1 plus 1/2 inverse Laplace of 1 over s minus 1. Which we're going to have to use the table. If you look at the table, you should be able to figure out the 1 over s minus 1 relatively easily. Based on the table, this inverse Laplace transform is going to be, this is the 1 over s minus a. That's going to be e to the, with a being 1, so e to the 1t. Can anyone help me find out what the inverse Laplace transform of 1 over s plus 1 is? Excellent, because that's really just the same, right? You can treat it as 1 over s minus a negative 1, with a negative 1 being the a. So this is really the same thing as inverse of 1 over s minus negative 1. So that will give us e to the negative t. Excellent. So that's in the end it's negative 3/2 e to the negative t plus 1/2 e to the positive t. Questions? So, if you kind of go back to the 3 steps, the first step, just have to be careful, figure out the right Laplace transform for each term there. The second step, I personally think is the easiest because you just solve for y of s. The last step, it's kind of, sometimes could be tricky. You're going to have to do some manipulation. You study S translation last lecture, right? You might have to use that. So there's something you have to do to make it into the form that you can actually apply the inverse Laplace transform. So that's kind of like the puzzling part. Any questions? Okay. All right. Let's look at another example quickly. Well, not quickly, but it's going to take a while. And then that should be enough. So we're going to solve initial value problem. This is example 2. Y double prime minus 4y prime minus 12y equals sine 2x. With the initial conditions. y of 0 equals y prime of 0 equals 0. So the first thing, we're going to take the Laplace transform of every term. So I'm going to not write down everything step by step. So what I'm going to do is I'm going to apply the Laplace transform to every term, but also pull out the constants. So I have Laplace transform of y double prime minus 4 Laplace transform of y prime minus 12 Laplace of y equals Laplace of sine 2, sorry, I'm going to change it to t. Doesn't matter, x of t, sine 2t. So if we use x, we're just going to stick with x all the way to the end. If we use t, we're going to use t all the way to the end. It doesn't really matter. Okay, so now we have this whole Laplace transforms. We just have to figure out what the corresponding expression based on the table or something we've seen here before. The first one is second derivative. We have s squared capital Y of s minus s times lowercase y of 0 minus lowercase y prime of 0. And then we have to find the correct Laplace transform of y prime based on the table. So negative 4 times, I believe it's s capital Y of s minus y of 0 based on the table. So you can always look at the table. Minus 12 times capital Y of s. That's the Laplace transform of just y, give you capital Y. And then the new part, something new is the sine 2t. If you remember that from the table, I'll have it memorized. The Laplace transform of sine kt will give us k over s squared plus k squared. So in this case, the k is equal to 2. So we're going to put 2 there, so 2 over s squared plus 2 squared. 2 over s squared plus 2 squared, which is 4. That's good, right? So we get rid of the differential equation. We can plug in the initial conditions. Those y of 0 equals 0, y prime of 0 also 0. So let's just get rid of anything that's a 0. So that's a 0, this is a 0, that's also 0. So we end up with the rest that's not non-zero, right? So let's just rewrite them. We get s squared, capital Y of s from the first bracket. Then we have negative 4 times s y of s minus 12 capital Y of s equals 2 over s squared plus 4. And then we're just going to solve for y of s from here. So s squared minus 4s minus 12, y of s equals 2 over s squared plus 4. And the y of s is equal to 2 over s squared minus 4s minus 12 times s squared plus 4. Any questions at this point? I feel like if you understand the big picture of the procedure, the first and second step usually, doesn't take very long. So that's the second step. We found the Laplace transform of lowercase y of t. We have to figure out what y of t is. So step 3, y of t equals inverse Laplace transform of this fraction, 2 over s squared minus 4s minus 12 s squared plus 4. And clearly, right, we couldn't figure out what the y of t is by just going to the table, because the table doesn't have a complicated expression like this. So that means we're going to have to try to use partial fractions from here. So we need to find partial fractions next for this fraction in the inverse Laplace transform. So in the future, if you were, let's say you were working on something like this, and you feel like you're going to end up with something complicated, you have to use partial fractions. So it's perfectly fine if you start factoring before you get to this point. For example, here you can just say, oh, I'm going to factor this first, because I'm probably going to use partial fractions. So if I factor that fraction, I end up with 2 over s minus 6, s plus 2. So if you're not comfortable with it, you should try to factor the denominator there, s squared plus 4. And with that, we can figure out the partial fractions. There should be 3 of them. So if we call this a over s minus 6, b over s plus 2, and the cx plus d over s squared plus 4. Well, before I move on further, can I ask, do you feel confident to go from here to this setup? Okay, good. And really, the rest is just being very careful not to make any mistakes to figure out those constants. And I hope it's okay if I'm being a little bit lazy, because I'm not going to, I just don't want to spend time like actually finding A, B, C, D step by step. I'm going to give them to you. Is that okay? Definitely give it a try on your own if you need more practice. So, but I'm pretty sure that you're going to get lots of practice of partial fractions from the homework problems. So at the end, a equals 1 over 160, b equals negative 1 over 32, c is equal to 1 over 40, and d equals negative 1 over 10. So the partial fractions, if I rewrite them, it's going to be a, so it's a 1 over 160 times 1 over s minus 6, plus b, which is negative, so negative 1 over 32 times 1 over s plus 2, cx plus d, so that would be 1 over 40 times x, plus negative, so it's minus 1 over 10, divided by s squared plus 4. And if you remember earlier, I said when we use partial fractions in Laplace transform at the end with Laplace transform, we have to split, sorry, we're going to have to split this last part, the last fraction. But let me fix the x. I just keep using x. So that would be c times s. This is 1 over 40 times s. There's no x here, just s. I apologize for the confusion there. So we're going to have to split the last fraction. I'm going to do that when I put into the inverse Laplace. So now we can solve for y of t. So y of t equals inverse Laplace transform of, so I'm going to rewrite this. So what's 1 over 160 times 1 over s minus 6 minus 1 over 32, 1 over s plus 2. I'm going to split the last fraction, so that's a 1 over 40 s over s squared plus 4. And then minus 1 over 10, 1 over s squared plus 4. over 10. And then we're just going to try to find the inverse Laplace of each one of them. So I'm going to rewrite it by pulling out all the constants for every corresponding term. So that will be inverse Laplace of, 1 over 160 times inverse Laplace of 1 over s minus 6 minus 1 over 32, and then inverse Laplace of 1 over s plus 2, and then plus 1 over 40, inverse Laplace of s over s squared plus 4, and then minus 1 over 10, inverse Laplace of 1 over s squared plus 4. Some of them are very straightforward. When you look at the table, you know immediately what it is. Some of them you might have to kind of trick things around a little bit to make it work. So, the sooner we get this done, the sooner I can let you go. Can you help me out here? So, what is so you can look at your table, you can look at your notes. What is the inverse Laplace of 1 over s minus 6? E to the 6t, right? Because it's minus 6, so it becomes a positive 6 in the exponent. So this is e to the 6t. So we get rid of the first inverse. What about the second one? The second one is inverse Laplace of 1 over s plus 2. Excellent, e to the negative 2t, great, good. How about the next one? Inverse Laplace of s over s squared plus 4. Excellent, so it'll be cosine of 2t, right? Whenever you have s over s squared plus a number, so that will be cosine, and then inside the cosine you're going to have to use the 4 there to find out the correct number, which is 2 squared, so that's 2t. Now last term, be careful, you obviously check the denominator, right? But you always have to make sure the numerator is correct. Any guess? It's okay if you get it wrong, don't worry.
1/2 times sine 2t.
It's 1/2 times sine 2t? Excellent, exactly. Where did this 1/2 come from?
Well, if it's a over s squared plus k squared.
Right.
Get rid of the 2 on top, it just goes 1 over s squared plus 4.
Exactly. So if you just think about this, you have k is 2, right? You should have a 2 in the numerator, but you don't. You only have 1. So that's what we have to make the numerator 2. So what I do is I just kind of think about this as, okay, I'm just going to force the numerator to be a 2, so 2 over s squared plus 4. So that will be in the correct form, right? 2 over s squared plus 2 squared, that's what this is. But since I'm changing the numerator to be 2, I have to undo the change, so multiply by half, to undo that extra 2 I added. But this half I have, I can just bring outside because it doesn't get involved when I do the inverse Laplace transform. So this half can go to the front, becomes half inverse Laplace of 2 over s squared plus 4. So that's why we have an extra half from this part. At least that's how I understand it. And then we can multiply with negative 1/10. And we already talked about that this part is just going to be sine 2t. So we have half sine 2t. And at the end, just write down the final step. So we got 1 over 160, e to the 6t, minus 1 over 32, e to the negative 2t, plus 1 over 40, cosine 2t, and then minus 1/10 times 1/2 1/20 sine 2t. Any questions on this? So I want to point out that I don't know if the table of Laplace transform will be provided when you have an exam on this material. Oh, good. Is that in the lecture? Okay. Well, that's a good thing. Then you don't have to memorize it. If it's not provided, then you kind of have to memorize it. Okay. Great. All right. If you don't have questions, I'll see you on Thursday. Take care.